Hi, this is Coach Hikel. Today I'm bringing you a podcast today over enzymes. Enzymes are another form of a protein. We talked about proteins are made up of chains of amino acids. Well, they make enzymes in a nutshell as well. So let's talk about why they're important and why we need them. First of all, we got to define what they are. So an enzyme are proteins. I just said that. They act as a catalyst. So what they do, they act as a catalyst. Okay? Well, a catalyst in literature happens to speed up the story or change the story dramatically. So enzymes are going to do kind of the same thing. They're not permanently changed. And that's kind of a three-dimensional globular shape. I call them a Pac-Man because they kind of look like Pac-Man. So they're specific for what they're going to catalyze, and I'll give you a few examples here pretty quick of why they're specific for what they're going to catalyze. They're reusable, and in this class, they're going to end in ASE. So if they end in an ASE, they're going to be an enzyme. So for example, sucrase is an enzyme that's going to break down sucrose. Lactase, again, is an enzyme. It ends in ASE, and it's going to break down lactose, which is a sugar that is found in milk. And then you're going to have maltase, which is going to break down maltose. Catch on to the pattern? Wonderful. Okay, so what they kind of do is they have an active site and a substrate. So this substrate is going to have to match the outer shape of this active site, or else it's not going to work. So they work by weakening the bonds, which in turn lower the activation energy. Okay, so they're going to lower the activation energy by weakening the bonds of a reaction. So imagine this is a reaction without an enzyme. Okay, so what you're going to have to do, you get to use all this energy to push it up this hill. Okay, then once you're going to get to the hill, the enzyme's going to start. So what an enzyme does is it comes in here and it's going to take this hill and it's going to decrease it. It's going to make the hill smaller so that the catalyzed pathway is actually going to happen faster or at the same speed, but it's going to use a lot less energy to do it. So the reference I always give my kids, and it seems to work out every year, is if you're going to IKEA from Little Elm High School, you can take 423 to 121 and you could get to IKEA. Or you could take the tollway to IKEA, but which way is going to get you there faster? Okay, the tollway is going to get you there faster, so it's your enzyme because you can reuse it. It doesn't change where you're going or how you got there, and it doesn't change the outcome of the reaction. Okay, so you can reuse it, it's reusable, it doesn't change the reaction, and it gets you there faster because it takes less energy or money, which gas is, $3.70 a gallon right now? So it's going to save you a lot of money by taking the tollway. So the tollway is going to be your enzyme to get to IKEA. So here's another chart, and this is just going to show you the hill's actually going to be lower on this. So without the enzyme is going to be in blue. See how it has to go up this big, large hill, and then the reaction finally starts? Well, the difference is when an enzyme comes in, is the activation energy is lowered. Okay, the red indicates the difference in the activation energy. So the substance or the reactant an enzyme acts upon is called the substrate. Okay, so here's your enzyme. That's going to be your substrate. They're going to match. Okay, your enzyme and substrate are going to match. They're both squares. So that substrate can easily bond with that enzyme. Okay, they're going to join together. Once they're joined together, it's going to be called the active site. It's the restricted region of the enzyme in which the molecule and the substrate bind together. So once they're bonded together, the enzyme now becomes active because it's an active site. So anytime the shape of an enzyme active site is changed, it's called an induced fit. Okay, it's induced by the substrate. So this changed, the two products changed from what the original reactant were. Okay, they have to come in here, they have to fit this, so the substrate is going to join in with the active site. It's going to change it. Okay, it's going to change it because it's going to create two different products. So think about lactase breaking down lactose into simpler sugars. These are the two lactose molecules that were broken down. They're changed by the substrate. So there's 4 things that affect how effective an enzyme works. So how much of it is available, how much of the substrate is available, temperature, and pH are going to be your 4 main ones. And the 2 that you see most often are going to be temperature and pH. There's also what's called cofactors and coenzymes, and then inhibitors. We're going to talk about inhibitors. We're not going to so much worry about cofactors and coenzymes in this class. That's more of a pre-AP and AP biology level. So we are going to talk about inhibitors. So high temperatures are the most dangerous types of reactions because they denature enzymes. So most enzymes like to be active at 98.6 degrees or your normal body temperature. So the reason you get a fever is because your body is trying to denature or disrupt the enzymes that are in those bacteria that are making you sick. Because most enzymes like to be around 6 to 8 on the pH scale. And all enzymes have an optimal temperature and optimal pH. They vary widely, but all have a very, very specific temperature which they like to act at. So inorganic substances such as zinc and iron and sometimes vitamins are also needed for proper enzymatic activity. For example, iron is present in hemoglobin in order for it to pick up oxygen. So that's an example of a cofactor or a coenzyme. This happens to be a cofactor of an enzyme, but that's for another day. So inhibitors. We're going to have to know basically the 2 basic types of inhibitors. The first one is called a competitive inhibitor. So competitive inhibitors, they resemble an enzyme substrates and they compete. They actively compete with the active site. So they are competitive. Okay, think about competitive. They're actively going to compete. So what it's going to do is, let's say the enzyme is this shape. Well, the substrate is going to be the same shape to join with the enzyme, but this competitive inhibitor is going to be so close to the original shape that they're still going to join, which is going to block this substrate from getting in here and doing its thing. A lot of your medicines are going to work like this. They're going to use competitive and non-competitive inhibitors to get the results that they need. So unlike a competitive inhibitor, non-competitive inhibitors aren't going to do anything with the active site. They're going to bond to another part of the enzyme, which is going to change the shape of the active site, which is going to block the combination of the substrate and the enzyme. So, okay, here's the enzyme. And I remember we used to have a little notch here. Well, what we did is we threw a non-competitive inhibitor on this side, which just changed the overall shape of the enzyme. So when the substrate comes in, it can't bond to the active site. And that's basically it for enzymes today, guys. I hope that clarified it up a little bit. I know that was really short and brief, but that's pretty much it. And as always, if you need any questions, please feel free to email me or ask me in class. And as always, have a great day. Bye.